Hi guys, greetings to you all. Welcome back to another lesson. Today we'll be looking at the equivalence relation. Now, talking about an equivalence relation, the first thing is that we need to look at a binary relation. And whenever we talk about a binary relation, it's a relation between two sets. And looking now at an equivalence relation, it's a relation on a set that is reflexive, symmetric, and transitive. These three properties must hold for a relation to be called an equivalence relation. So to show these three properties, first we have a relation that can be R, then we have it on a set. Now, when you talk about a relation being reflexive, what does that mean? If we are on R, to check the reflexive property, say relation is reflexive. A relation that is reflexive, it means when we have our relation R on a set A, it means A relates to A for all A that belong to that set. It is related to itself. So that the relation is reflexive because it is related to itself. Now, the second property to be verified, which is symmetric on the relation describes symmetric. If it is symmetric, when a relation is symmetric, it means when we have A, B, for all A, B belonging to the set, that set, and a relation R, if A relates B, then B relates A. If A relates B, then B relates A. Very important. Which means this is what we assume. This A relates B is the ingredient that we have. I will use it to prove that B relates A. Now, the third property that we look at is transitivity. A relation is said to be transitive. Relation R is transitive on a set A if for all A, B, C that belongs to the set A, for all A, B, C that belongs to the set A, okay, A, B that belongs to the set A relates B, and B relates C, then A relates C. So this is what we have. A relates B, B relates C. Now we'll be required to show that A relates, and when that is done, the relation is transitive, a transitive relation. That of transitivity. That's why we say the relation of friendship is not transitive. Because if Mary is a friend to John, and John is a friend to Lawrence, it does not mean that Mary is a friend to Lawrence. Friendship is not transitive. Okay, that said, having known the three properties, we'll go straight to examples, solved examples. Now, example 1. The relation R on the set of integers is defined by, let's see how the relation is being described. It's defined by A relates B if and only if A plus B is an even number. Now, what does it mean being an even number? An even number simply means it's a multiple of 2. A relates B if and only this. Let's describe that relation. A relates B if and only if A plus B is even. That is means it's 2n, where n belongs to what? Z. Whenever you say it is even, it's an even number, it's a multiple, it's 2n. But if the question said it's an odd number, then we are going to use 2n plus 1. If they say it's a multiple of 3, we use 3n, 3m. Alright. Now, this is the relation that has been described. We are going to go straight away to show that it is, verify if it is 1. Let's check about reflexive. Is it reflexive? Let's verify reflexivity, whether it is reflexive. Okay, we take an A in the set of integers, any number A. If you have A here belong to Z, you see A relates A. According to this relation, A relates B if and only A plus B is equal to a multiple of 2. A relates A, we just replace A, means A plus what? A, and which is 2A. This is a multiple. 2A is already showing that it's an even number. So we say that the relation is reflexive. Hence, R is reflexive. Okay. We verify symmetry. Symmetry. Symmetry says A be here belonging to Z. If A relates B, we are required to show that we are required to prove that B relates A. Okay. Now A relates B. What does that mean? A relates B implies that A plus B is equal to 2n. How then do we show that B relates A? Now from this, A relates B, we use it to prove that B relates A. And B relates A simply means it will be B plus A is equal to 2n. A plus B can still be written as B plus A, since addition is commutative. So A plus B is equal to 2n is still the same as B plus A is 2n, which implies that B relates A. Hence, R is symmetric. R is symmetric. Now, we verify another important property, which is transitivity. That's verifying whether it is transitive. And to do that, we have A relates B. Say if and only if A plus B is equal to what? 2n. Another condition that we use is that B relates C. So B relates C means B plus C is equal to 2m. Here n belongs to Z. Here m belongs to Z. Now we are required to show that we need to prove that A relates C. We need to prove that A relates C. Okay. need to prove that A relates. Now, from this, I got this equation 1 and this equation 2. Let's add it and see what happens. Because we have these two, we are going to use it to prove that A relates C. So adding these two, adding 1 plus 2, we have A plus 2B plus C is equal to 2m plus 2n. 2n plus 2. Now when we rearrange, you have A plus C is equal to 2n plus 2m minus 2b, okay, which is equal to 2 into n plus m minus b, which is simply a certain 2t, where t is n plus n minus b. This implies what? This implies A plus C is 2t, so it's even. This implies A relates. And we are done. So we have proven that it is transitive. So we conclude that since it is transitive, since it is reflexive, symmetric, and transitive, thus it is an equivalence relation. Okay. Now, but if you're asked to show that it is not an equivalence relation, take note that it will just need one. When one of the conditions fails, you can stop. Okay. When one of the conditions fail, we can stop. All right. Thank you. See you in the next video.